Yo, yo, yo. Give me a second. Give me a second. Second. Yo, 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 yo. Check it out. Check it out. Whoa, whoa. It's fucking early in the morning. கொஞ்சம் linear algebra. I'm gonna. Let's see. I think this is the last thing that I have read or studied or whatever. Let's do a summary real quick. Orthogonal Grand Schmidt. This is the last thing that I've studied, so I can actually check here. Maybe not. Yeah, all of this shit can go. Whoa, wait, why? Some of the stuff are like really important, I think. Yeah, these two are like really good. Interrogation. Okay, என்ன பண்ண போறேன்னா this thing, orthogonal matrices and Graham Schmidt. So much to fucking do.
The barrier for entry into web scraping is higher than ever.
Well, this should copy. Okay, it copies. What the fuck was that then? Let's hear from this dude first.
Professor Dave here. I want to teach you the Graham Schmidt process.
Brother, get this intro out of here, man. Are we like fucking in? Know what I mean?
Professor
Second
Dave
grade.
here. I want to teach you the Graham Schmidt process. He knows a lot about all kinds of stuff. Professor Dave explains. In the previous tutorial, we learned all about
Something about his negative Cantor tilt. Something about it just reveals a lot of information about him, you know.
orthogonal vectors and how we can generate from these a set of orthonormal vectors by taking each vector and dividing it by its length. This makes each vector's length equal to 1. And since they were already orthogonal, the new vectors become orthonormal. But what if we start with a set of vectors that are not already orthogonal? Furthermore, how do we go about making an orthonormal basis for a vector space, given any set of vectors that form a basis? To do this, we need to learn something called the Graham Schmidt process. So let's take a look at this now. To see how this works, let's examine the vectors v1 to vn, which serve as a basis for the vector space V. Our only requirement for these vectors is that they form a basis. We are no longer assuming any orthogonality between them. The Graham Schmidt process takes these vectors and forms a new orthogonal set of basis vectors, which we will label u1 to un. The process goes as follows. First, start by setting the first new vector u1 equal to the first basis vector v1. For the second step, take the second vector v2 and subtract from it the inner product between v2 and u1, divided by the length of u1 squared times the vector u1. So altogether, that looks like this.
Brother, what the fuck? Brother, what the fuck are you talking? Let's hear from this guy. I'm gonna grab some coffee and grab some water real quick. In the back. Mathematics. Mathematics is fun.
I want to talk to you about how to find an orthonormal basis for a vector space or for a subspace of a vector space. For example, this purple plane here, that's a subspace of R3. And it is going through the origin, so that does indeed make it a subspace of R3. It's not just any other plane. And maybe my goal is to find an orthonormal basis for it. It certainly has a basis of two vectors, but I want an orthonormal basis. So the reason I might want to do that, let me hide the axes here. I might have a vector here, this white vector, and I want to project it onto that purple plane. And there's a pretty straightforward way of doing that if indeed I have an orthonormal basis for that purple plane. It just involves doing a couple projections onto the basis vectors. That of course looks like this. The projection vector would be this, and its perpendicular component would
Yeah, projection is basically, it's like a shadow, right?
be this, and the point is how do I get these two blue vectors from that white one? And again, if I have an orthonormal basis for the purple plane, there's a way of doing that. So, but the problem is that it might not be totally obvious how to get an orthonormal basis, but it might be rather straightforward to get any old basis for this purple plane. I might have already been given that. Maybe that's how the plane was described. Or maybe if I had an equation for the plane, I could do a little arithmetic and try to find a couple vectors which are a spanning set for that plane. But you can see if I come up with, say, two basis vectors, say these two green ones, they're not orthogonal to each other, and they're probably not even of length 1. So they're not an orthonormal basis, but they are a basis. And the question is, can I work with that somehow? Can I kind of coax those into being an orthonormal basis by altering them in some way? So there's a way of doing that, but let me show you how that works in 2 dimensions here. It's easier to see what's happening if we do it in 2D. So let's move here to 2D. I have two vectors here, v1 and v2. Those are indeed a
What is orthogonal? Bro, I have like so much tabs open up. It's crazy. So much tabs. Let's get this here. Means intersection or lying on a right angle. So that's what I mean, right angle. Upright angle. Upright angle. Okay.
basis for R2. Of course, we already have an obvious orthonormal basis for R2. That's E1 and E2, 1, 0, and 0, 1. But the point is, I want to think about that more general situation where I have a basis already and I want to try to tweak it somehow and kind of convert it or get an orthonormal basis from that. So let's start with having V1 and V2 here and see if I can kind of alter them in some way to get an orthonormal basis. So V1 and V2 are the vectors as shown. Those are not of length 1. V1 has length, what is that, square root of 10, I think? And they're not even orthogonal to each other either. So here's the process. Now let me get rid of the labels here. I don't really want to think about the numbers so much. I want to just think about the geometry of this. And let's go through the idea. What we're going to do is we're going to keep V1. This vector V1, we're going to hang on to that one. We're going to keep that in our basis, except it's not of length 1, so I have to fix that. Its length is square root of 10 right now or something like that. So what I'm going to do is I'm going to shorten it. I'm going to shorten it down to a unit vector. And you would say you're normalizing the vector when you do that. So you know how to do that. You multiply by 1 over the magnitude, and that would convert it to this orange vector here. So then let me get rid of V1. So I'm replacing it with U1. So U1 is just a shortened version of V1. And then what we're going to do is we're going to take V2 and we're going to extract out of that something which is orthogonal to U1, and that'll be our other basis vector. What's kind of important right now about V2 is that it's not parallel to U1. It couldn't be because V1 and V2 are a basis for R2. So V2 is definitely not parallel to U1. that means that v2 has a parallel component to u1 and a perpendicular component to to u1, which is non-zero. So you know how to do this. I'm going to project v2 down onto the u1 vector. I guess what
So it is gonna be, yeah,
I really mean when I say that,
The
when we
cross
say we're
product.
projecting a vector onto another, is
similar
we're
to a
projecting
cross product.
the blue vector down onto the space spanned by u1, this line here. So that would look something like this. We drop a perpendicular down, and this is geometrically what's happening. And then the projection vector looks like this. This green vector here is the projection of the v2 onto the line spanned by u1. And then the perpendicular component of that is obtained by subtraction, right? We're just going to take v2 and subtract off its perpendicular component, and then we have v2 perpendicular there. No, if I said that right. We're going to subtract the parallel component from v2 to get the perpendicular component of v2. And that's it. This is going to be our vector that we're going to use for the basis, v2 perpendicular. Let me draw that, though, over coming out of the origin, because that might be a better place to see it.
Ooh,
Hide some of these other components here.
Look at that.
And u1 and v2 perpendicular are now indeed orthogonal to each other, and they serve as a base.
So this vector is orthogonal to these two vectors. I wonder what we can do with that. So I think it's similar to like how like particles like reflect and shit like that. I don't know, something like that. Everything is like connected to everything else. You know, it's that's the good part about science, isn't it?
For R2, there's only one last thing to do. V2 perpendicular is not of length 1, and it's an easy conversion to normalize that. You divide by its length, and you get a vector, which is indeed of length 1, and that would give us a vector we can call U2. So now U1 and U2 are both of length 1, and they're perpendicular to each other, so they are an orthonormal basis for R2. And again, remember how we did that. We started with two vectors, v1 and v2.
Yeah.
This L here. We started with v1 and v2, and we kind of coaxed them into giving us an orthonormal basis for R2.
Yep.
We kept v1.
I remember this video.
And then we took the part of v2, which was perpendicular to that first u1. And that's called the Gram-Schmidt orthogonalization process for getting an orthonormal basis, starting from some other basis that you have. So now remember that these vectors were very specific. v1 and v2 had specific components to them. Maybe you can kind of go back, watch the video again, and see if you can actually work out.
Bro, this fucking guy, bro. Fucking idiot, bro. Don't like him at all. A linear discrete dynamic system and its eigenvector. Okay. We're losing the plot here. What are we doing? What are we doing? Analyzing beats? Okay.
Okay, here's the last lecture in the chapter on orthogonality. So we met orthogonal vectors, two vectors.
Yeah.
We met orthogonal subspaces, like
Yeah.
the row space and null space. Now, today we meet
Hmm.
an orthogonal basis and an orthogonal matrix. So we really, this chapter cleans up orthogonality. And really, I should use the word orthonormal. Orthogonal is, so my vectors are Q1, Q2 up to Qn. Can I use the letter Q here to remind me I'm talking about orthogonal things? Not just any vectors, but orthogonal ones. So what does that mean? That means that every Q is orthogonal to every other Q. The natural idea. To have a basis that's headed off at 90-degree angles, the inner products are all zero. Of course, if Q is, certainly Qi is not orthogonal to itself, but there we'll make the best choice again, make it a unit vector. Then Qi transpose Qi is 1 for a unit vector. The length squared is 1, and that's what I would use the word normal. So ortho for this part, normal, normalized, unit length for this part. Okay, so first part of the lecture
Orthogonal, orthonormal
is, how does
vectors.
having an orthonormal basis make things nice? It certainly does. It makes
So, yeah, orthonormal basis basically means, say, toy, and we have unit 1 vector, maybe not there, unit 1 vector basis over here, and the orthonormal would be like over here, I think. This will be the orthonormal vectors, I believe. So let's say I want to project project this shit on this vector. This is how it will go. Right. And this will be the U1, V2, I mean V1. This will be V2 projection, and will be V1 by 2, whatever that means. And the actual orthonormal vector would be this one. So U2. Yeah. That's the recap on what we saw.
all the calculations better. A whole lot of numerical linear algebra is built around working with orthonormal vectors because they never get out of hand. They never overflow or underflow. And I'll put them into a matrix Q. And then the second part of the lecture will be, suppose my basis, my columns of A, are not orthonormal. How do I make them so? And the two names associated with that simple idea are Graham and Schmidt. So the first part is, we've got a basis like this. Let's put the...
Bro, I hate these like fuck ass like names, Graham and Smith. You know what I mean? Make it like combine that shit and make it something like unique. You know what I mean? Like
Let's put those into the columns of a matrix. So
make it like, I don't know. Take this shit, GRA, and combine with this. So it'd be like Grammet. You know what I mean? Grammet matrix. Instead of all this like fuck ass like Graham and Schmidt. Shut the fuck up.
so a matrix Q that has, I'll put these orthonormal vectors. Q1 will be the first column. Qn will be the nth column.
Yeah.
And I want to say, I want to write this property, Qi transpose Qj, being 0. I want to put that in a matrix form. And just the right thing is to look at Q transpose Q. So this chapter has been looking at A transpose A, so it's natural to look at Q transpose Q, and the beauty is it comes out perfectly. Because Q transpose has these vectors in its rows. The first row is Q1 transpose, the nth row is Qn transpose, so that's Q transpose. And now I want to multiply by Q, that has Q1 along to Qn in the columns. That's Q. And what do I get? Really, this is the first, simplest, most basic fact, that how do orthonormal vectors, orthonormal...
So what are we doing? We're getting the orthonormal vector 1 and transposing. How does even transpose look like? I keep forgetting it. How does transpose look like? What is a transpose? What is a transpose? What the fuck is a transpose? 2 by 2 Q. I want a 2 by 2 matrix, bro. Don't want this 3 by 3 shit. Oh, fuck's sake. Brother, give me a 2x2 matrix, brother. How the fuck do I get that? Bro, give me a 2x2 matrix. Okay, how do I do? Is linear transformation? What even is transformation? Who knows? Like linear transformation. Fuck ass linear transformation.
columns in a matrix. What happens if I compute Q transpose?
I'm trying to think, like, what is Q? Like, okay, we got an orthogonal matrix, and the transpose of that. It's not really an orthogonal, but chick, and we got a transpose of that. What do we get? What do we get? What do Will we get like a orthogonal? You get an orthogonal subspace, probably. Null vector, null space.
Do you see it? If I take the first row times the first column, what do I get? A 1. If I take the first row times the second column, what do I get? 0. That's the orthogonality. The first row times the last column is
just
0.
identity
And so I'm
vector.
getting 1s on the diagonal, and I'm getting 0s
Who
everywhere
would have
else.
thought?
I'm getting the identity matrix.
Who would have thought?
You see how that's it's just like the right calculation.
I thought it was like a trick question. I thought he was gonna be like, it's not gonna be an identity vector matrix, you know? It's like, yeah, this is not gonna be an identity because it's like a thing. I thought he was gonna like juke us with this question, but for fuck's sake, it's the same
Orthogonal
identity.
columns. And the matrix doesn't have to be square here. We might have just 2 columns.
So how does it actually work? Let's see. Let's see this thing. So I want this over here. Yeah, it's a identity matrix, yeah. Bro, can I like, don't you guys have like the lock-in thing? Can you not lock in this shit for me? Please, lock in, like, yeah. Lock in, gang. Lock in, gang. What is missing? Brother, everything is perfect, brother, except this shit. Okay, yeah, that is the transpose of the thing. So when when that t, whatever t is, reaches let's show determine. I mean, determine is gonna like stay the same, I think. Yeah, it's interesting, isn't it? Like it's cuts through the middle of the orthogonality. I'm so smart. Does it still cut in the middle? Oh wait, what? So it doesn't have a. Interesting.
And they might have 4, lots of components. So, but they're orthonormal. And when we do Q transpose times Q, that Q transpose times Q, or A transpose A, just asks for all those dot products. Rows times columns. And in this orthonormal case, we get the best possible answer, the identity. Okay, so this is like, so, I mean, now we have a new bunch of important matrices. what have we seen? Previously. We've seen in the distant past we had triangular matrices, diagonal matrices, permutation matrices. That was early chapters. Then we had row echelon forms. Then in this chapter we've already seen projection matrices. And now we're seeing this new class of matrices with orthonormal columns. That's a very long expression. I am sorry that I can't just call them orthogonal matrices. But that word orthogonal matrices, or maybe I should be able to call it orthonormal matrices. Why don't we call it orthonormal matrices? I mean, that would be an absolutely perfect name for Q. Call it an orthonormal matrix because its columns are orthonormal. Okay, but the convention is that we only use that name, orthogonal matrix. We only use this word, orthogonal, we don't even say orthonormal for some unknown reason, matrix, when it's square. So in the case when this is a square matrix, that's the case we call it an orthogonal matrix. And what's special about the case when it's square? When it's a square matrix, we've got its inverse. So in the case if Q is square, then Q transpose Q equals I tells us, let me write that underneath, tells us that Q transpose is Q inverse. There we have the easy to remember property for a square matrix with orthonormal columns. I need to write some examples down. Let's see. Some examples, like if I take any permutation, some examples. Let's do some examples. Any permutation matrix. Let me take just some random permutation matrix. Permutation. Q equals, let's say, I'll make it 3 by 3, say 0, 0, 1, 1, 0, 0, 0, 1, 0. Okay. That certainly has unit vectors in its columns. Those vectors are certainly perpendicular to each other. And and so that's it. That makes it a Q. And if I took its transpose, if I multiplied by Q transpose, shall I do that? Let me stick in Q transpose here. Just to do that multiplication once more. Transpose will make that into a column, make that into a column, make that into a column. And the transpose is also another Q, another orthonormal matrix. And when I multiply that product, I get I. Okay, so there's an example. And actually, there's a second example. But those are really easy examples, right? I mean, to get orthogonal matrices, orthogonal columns by just putting ones in different places is like too easy. So let me keep going with examples. So here's another simple example. Cos theta, sine theta. There's a unit vector. Oh, let me even take it. Well, yeah. Cos theta, sine theta. And now the other way, I want sine theta, cos theta. But I want the inner product to be 0. And if I put a minus there, it'll do it. So that's a unit vector. That's a unit vector. And if I take the dot product, I get minus, plus, 0. Okay. So for example, Q equals, say, 1, 1, 1, minus 1. Is that an orthogonal matrix?
No.
I've got orthogonal columns there, but it's not quite an orthogonal matrix. How shall I fix it to be an orthogonal matrix? Well, what's the length of those column vectors? The dot product with themselves is, right now it's
0.
2, right?
Okay.
The length squared. The length squared would be 1 plus 1 would be 2. The length would be square root of 2, so I better divide by square root of 2. Okay. So now I have got an orthogonal matrix. In fact, it's this one when theta is pi over 4. The cosines and sine, well, almost. I guess the minus sign is down there. So maybe, I don't know, maybe minus pi over 4 or something. Okay. Let me do one final example, just to show that you can get bigger ones. Q equals, let me take that matrix up in the corner, and I'll sort of repeat that pattern. Repeat it again, and then minus it down here. That's one of the world's favorite orthogonal matrices. I hope I got it right. Can you see whether, if I take the inner product of one column with another one, let's see. If I take the inner product of that column with that, I have 2 minuses and 2 pluses, that's good. When I take the inner product of that with that, I have a plus and a minus and a plus, good. I think it all works out. And what do I have to divide by now to make those into unit vectors? Right now, the vector 1, 1, 1, 1 has length 2, square root of 4. So I have to divide by 2 to make it unit vector. So there's another. That's my entire array of simple examples. This construction is named after a guy call Hadamard, and We know how to do it for 2, 4, 16, 64, and so on, but nobody knows exactly which size matrices have which sizes allow orthogonal matrices of 1s and -1s. So an Adamard matrix is an orthogonal matrix that's got 1s and -1s, and a lot of ones, some we know, some other sizes, there couldn't be a 5 by 5, I think, but there are some sizes that nobody yet knows whether there could be or can't be a matrix like that. Okay, you see those orthogonal matrices.
Interesting.
Now, let me ask, why is it good to have orthogonal matrices? What calculation is made easy if I have an orthogonal matrix? And let me...
What calculation is made easy? It's gotta be, so let's take a orthogonal matrix.
Let me remember that the matrix could be rectangular. So I put down I better put a rectangular example down. So these are all square examples. Can I put down just a rectangular one just to be sure that we realize that this is possible? Let's help me out. Let's see. If I put like a 1, 2, 2, and -2, -1, 2. That's a matrix. Oh, its columns aren't normalized yet. I always have to remember to do that. I always do that last because it's easy to do. What's the length of those columns? So if I wanted them to be length 1, I should divide by their length, which is, so I look at 1 squared plus 2 squared plus 2 squared. That's 1 and 4 and 4 is 9. So I take the square root and I need to divide by 3. Okay, so there is, well, without that, I got one orthonormal vector. I mean, just one unit vector. Now, put that guy in. Now I have a basis for the column space, for a two-dimensional space, an orthonormal basis, right? These two columns are orthonormal. They would be an orthonormal basis for this two-dimensional space that they span. Orthonormal vectors, by the way, have got to be independent. It's easy to show that orthonormal vectors, since they're headed off all at 90 degrees, there's no combination that gives 0. Now, if I wanted to create now a third one, I could either just put in some third vector that was independent and go to this Gram-Schmidt calculation that I'm going to explain, or I could be inspired and say, look, with that pattern, why not put a 1 in there, and a 2 in there, and a 2 in there, and try to fix up the signs so that they work. I don't know if I've done this too brilliantly. Let's see, what signs? That's minus. Maybe I'd like a minus sign there. How would that be? Yeah, maybe that works. I think that those three columns are orthonormal, and the beauty of this is the last example I'll probably find, where there's no square root. The punishing thing in Gram-Schmidt, maybe we better know that in advance, is that because I want these vectors to be unit vectors, I'm always running into square roots. I'm always dividing by lengths, and those lengths are square roots. So you'll see, as soon as I do a Gram-Schmidt example, square roots are going to show up. But here are some examples where we did it without any square roots. Okay, so great. Now next question is, what's the good of having a cube? What formulas become easier? Suppose I want to project, so suppose Q has orthonormal columns. I'm using the letter Q to mean this. I'll write it this one more time, but I always mean, when I write a Q, I always mean that it has orthonormal columns. So suppose I want to project onto its column space. So what's the projection matrix? What's the projection matrix if I project onto a column space? Okay, that gives me a chance to review the projection section. including that big formula, which used to be have those 4 A's in a row, but now it's got Q's because I'm projecting onto the column space of Q. So do you remember what it was? It's Q transpose Q inverse, Q transpose. That's my 4 Q's in a row. But what's good here? What makes this formula nice if I'm projecting onto a column space when I have orthonormal basis for that space? What makes it nice is this is the identity. I don't have to do any inversion. I just get Q transpose. So Q transpose is a projection matrix. Oh, I can't resist just checking the properties. What are the properties of a projection matrix? There are 2 properties to know for any projection matrix. And I'm saying that this is the right projection matrix when we've got this orthonormal basis in the column. Okay. So there's the projection matrix. Suppose the matrix is square. Just tell me first this extreme case. If my matrix is square and it's got these orthonormal columns, then what's the column space? If I have a square matrix and I have independent columns and even orthonormal columns, then the column space is the whole space, right? And what's the projection matrix onto the whole space? The identity matrix. If I'm projecting the whole space, every vector B is right where it's supposed to be, and I don't have to move it by projection. So this will be I. This is I'll put in parentheses. This is I if Q is square. Well,
okay.
we said that already. If Q is square, that's the case where Q transpose is Q inverse. We can put it on the right. We can put it on the left. We always get the identity matrix. If it's
Even
square.
if it's in rectangle. Yeah. That doesn't make any sense though. Even if it's in rectangle, let's say. So we have one of these. Multiply one of these. Will be identity, yeah? Why not? Maybe not in every case.
But if it's not a square matrix, then it's not. We don't get the identity matrix. We have Q transpose. And just, again, what are those 2 properties of a projection matrix? First of all, it's symmetric. Okay, no problem. That's certainly a symmetric matrix. So what's that second property of a projection? That if you project and project again, you don't move the second time. So the other property of a projection matrix should be that Q transpose twice should be the same as Q transpose once. That's projection matrices. And that property better fall out right away because from the fact we know about orthonormal matrices, Q transpose Q is I. Okay, you see it. In the middle here is sitting Q transpose Q. Sorry, that's what I meant to say. Q transpose Q is I. So that's sitting right in the middle. That cancels out to give the identity. We're left with 1 Q transpose, and we're all set. Okay, so this is the projection matrix. All the messy equations of this chapter become trivial when we have this orthonormal basis. I mean, what do I mean by all the equations? Well, the most important equation was the normal equation. You remember old A transpose A x hat equals A transpose B? But now A is Q. Now I'm thinking I have Q transpose Q x hat equals Q transpose B. And what's good about that? What's good is that matrix on the left side is the identity. The matrix on the left is the identity, Q transpose Q. Normally it isn't. Normally it's that matrix of inner products, and you've got to compute all those dopey inner products and solve the system. Here, the inner products are all 1 or 0. This is the answer on, and there's the answer. There's no inversion involved. Each component of X is a Q times B. What that equation is saying is that the ith component is the ith basis vector times B. That's probably the most important formula in some major parts of mathematics. That if we have orthonormal basis, then
What the fuck?
component in the ith along the ith, the projection on the ith basis vector is just Qi transpose B. That number X that we look for is just a
Write
dot
that
product.
on my hand.
Okay, so I'm ready now for the sort of like second half of the lecture, where we don't start with an orthogonal matrix or orthonormal vectors. We just start with independent vectors, and we want to make them orthonormal.
So yeah, he's gonna take a U and make this shit happen. You wanna make that shit happen. You too. Let's see. This is the actual thing.
Can I do that now? Now here comes Graham Schmidt.
Yeah,
So
Graham
Graham
Schmidt.
So this is a calculation. I can't quite say it's like elimination, because it's different. Our goal isn't triangular anymore. With elimination, our goal was make the matrix triangular. Now our goal is make the matrix orthogonal. Make those columns orthonormal. So let me start with 2 columns. So I start with vectors A and B. And they're just like, here, let me draw them. Here's A. Here's B. For example, A isn't specially horizontal, wasn't meant to be. Just A is one vector, B is another. I want to produce those 2 vectors. They might be in 12-dimensional space, or they might be in 2-dimensional space. They're independent anyway. So I better be sure I say that. I started with independent vectors. And I want to produce out of that Q1 and Q2. I want to produce orthonormal vectors. And Graham and Schmidt tell me how. Okay. Well, actually, you could tell me how. We don't need, frankly, I don't know. There's only one idea here. If Graham had the idea,
Projection.
I don't know what Schmidt did. But, okay, you'll see it. We don't need either of them, actually. Okay, so what am I going to do? I'll take this first guy. Okay. Well, he's fine. That direction is fine, except, yeah, I'll say, okay, I'll settle for that direction. So I'm going to get, so what am I going to, my goal is, I'm going to get orthogonal vectors, and I'll call those capital A and B. So that's the key step, is to get from any two vectors to two orthogonal vectors. And then, at the end, no problem, I'll get orthonormal vectors. Those will be my Q's, Q1 and Q2. And what will they be? Once I got A and B orthogonal, well, look, it's no big deal. Maybe that's what Schmidt did. Brilliant Schmidt, thought, okay, divide by the length. All right. That's Schmidt's contribution. Okay.
Whoa, mind blown.
But Graham had a little more thinking to do, right? We haven't done Graham's part. This part, except, okay, I'm happy with A. A can be A. That first direction is fine. No complaint about that. The trouble is the second direction is not fine, because it's not orthogonal to the first. I'm looking for a vector that starts with B, but makes it orthogonal to A. What's the vector? How do I do that? How do I produce from this vector a piece that's orthogonal to this one? And remember, these vectors might be in 2 dimensions or they might be in 12 dimensions. I'm just looking for the idea.
Projection onto the
Where did we
vector.
have orthogonal,
That's how you do
a
it.
vector showing up that was orthogonal to this.
That's how real G's do it. I need to take a piss. So
Well, that was the first basic calculation of the whole chapter. We did a projection, and the projection gave us this part, which was the part in the A direction. Now, the part we want is the other part, the E part, this part. This is going to be our, that guy is that guy. This is our vector B, that gives us that 90-degree angle. So B is, you could say, B is really what we previously called E, the error vector. And what is it? I mean, what is B here? A is A, no problem. B is, okay. What's this error piece? Do you remember? It's I start with the original B, and I take away what? Its projection, this P. The vector B, this error vector, is the original vector removing the projection. So instead of wanting the projection, now that's what I want to throw away. I want to get the part that's perpendicular. And there will be a perpendicular part. It won't be 0. Because these vectors were independent. So if B was along the direction of A, then if the original B and A were in the same direction, then I've only got one direction. But here they're in 2 independent directions, and all I'm doing is getting that guy. So what's its formula? What's the formula for that? I want to subtract the projection. So do you remember the projection? It's some multiple of A. And what's that multiple? It's that thing called X in the very, very first lecture on this chapter. There's an A transpose A in the bottom. And there's an A transpose B. Isn't that it?
what the fuck?
I think that's Graham's formula. Or Graham-Schmidt. No, that's Graham. Schmidt has got to divide the whole thing by the length. So his formula makes a mess, which I'm not willing to write down. So let's just see that. What am I saying here? I'm saying that this vector B is perpendicular to A. That these are orthogonal. A is perpendicular to B. Can you check that? How do you see that? Yes, of course, our picture is telling us, yes, we did it right. How would I check that this matrix is perpendicular to A? I would multiply by A transpose, and I better get 0, right? I should check that. A transpose B should come out 0. So this is A transpose times, now what did we say B was? We start with the original B, and we take away this projection, and that should come out 0. Well, here we get an A transpose B, minus. And here's another A transpose B, and it's an A transpose A over A transpose A, a 1, those cancel, and we do get 0. Right. Now, I guess I can do numbers in there, but I have to take a third vector to be sure we've got this system down. So now I have to say, if I have independent vectors A, B, and C, I'm looking for orthogonal vectors A, B, and capital C, and then, of course, the third guy will just be C over its length, the unit vector. So this is now the problem. I got B here. I got A very easily. And now, if you see the idea, we could figure out a formula for C. So now that so this is like a typical homework quiz problem. I give you 2 vectors, you do this. I give you 3 vectors, and you have to make them orthonormal. So you do this again. The first vector is fine. The second vector is perpendicular to the first, and now I need a third vector that's perpendicular to the first one and the second one, right? This is the end of the lecture, is to find this guy. Find this vector C that's perpendicular. At this point, we know A and B. But C, the little c that we're given, is off in some. It's got to come out of the blackboard to be independent. So can I sort of draw off? Off comes a C somewhere. I don't know, where am I going to put the darn thing? Maybe I'll put it off. Oh, like that somehow. C, little c. And I already know that perpendicular direction, that one and that one. So now, what's the idea? Give me the Gram-Schmidt formula for C. What is this C here? Equals what?
Let me think.
Give me the Gram-Schmidt formula for C. What is this?
It's gotta be the projection of A and B onto C. No. It's what the fuck am I saying? So it is the orthogonal. What am I saying? What am I saying?
Equals what? What am I going to do? I'll start with the given one, as before, right? I start with the vector I'm given. And what do I do with it? I want to...
Yeah, you want to take the vector that you're given minus the projection of A and B.
remove out of it. I want to subtract off. So I'll put a minus sign in. I want to subtract off its components in the capital A and capital B directions. I just want to get those out of there. Well, I know how to do that. I did it with B, so let me take away. What if I do this? What have I done? I've got little c, and what have I subtracted from it? Its component, its projection, if you like, in the A direction. And now I've got to subtract off its component, B transpose C, or B transpose B.
Hell yeah.
Is its component in the B direction. And that gives me the vector capital C that, if anything is, if there's any justice, this C should be perpendicular to A, and it should be perpendicular to B. And the only thing it hasn't got is unit vector, so we divide by its length to get that too. Okay. Let me do an example. I'll make my life easy. I'll just take two vectors. So let me do a numerical example. If I'll give you two vectors, you give me back the Gram-Schmidt orthonormal basis, and we'll see how to express that in matrix form. Okay. So let me give you the two vectors. So I'll take the vector A equals, let's say, 1, 1, 1. Why not? And B equals, let's say, 1, 0, 2. Okay. I didn't want to cheat and make them orthogonal in the first place, because then Gram-Schmidt wouldn't be needed. Okay, so those are not orthogonal. So what is capital A? Well, that's the same as big A. That was fine. What's B? So B is the original B, and then I subtract off some multiple of the A. And what's the multiple? What goes in here? B, here's the A. This is the little b. This is the big A, also the little a. And I want to multiply it by that right ratio, which has A transpose A. Oh, here's my ratio. I'm just doing this. So it's A transpose B. What is A transpose B? It looks like 3. And what is A? Oh my. What's A transpose A? 3. I'm sorry. I didn't know that was going to happen. Okay, but it happened. Why should we not? Okay, so do you see it all right? That's A transpose B. There's A transpose A. That's the fraction. So I take this away, and I get 1 take away 1 is a 0. 0 minus this 1 is a minus 1. And 2 minus the 1 is a 1. Okay, and what's this vector that we finally found? This is B. And how do I know it's right? How do I know I've got a vector I want? I check that B is perpendicular that A and B are perpendicular. That A is perpendicular to B. Just look at that. That one, the dot product of that with that is 0. Okay, so now what is my Q1 and Q2? Why don't I put them in a matrix? Of course, since I'm always putting these. So I'll put the Q1 and the Q2 in a matrix. And what are they? Now, when I'm writing Q's, I'm supposed to make things normalized. I'm supposed to make things unit vectors. So I'm going to take that A, but I'm going to divide it by square root of 3. And I'm going to take this B, but I'm going to divide it by square root of 2 to make it a unit vector. And there is my matrix. That's my matrix with orthonormal column coming from Gram-Schmidt, and it came from the original 1, 1, 1, 1, 0, 2, right? That was my original, guys. These were the two I started with. These are the two that I'm happy to end with, because those are orthonormal. So that's what Gram-Schmidt did. Well, tell me about the column spaces of these matrices. How is the column space of Q related to the column space of A? So I'm always asked.
It is orthogonal,
and that makes
isn't
you
it?
think, okay, the column space is all combinations of the columns. It's that plane, right? I've got two vectors in three-dimensional space. Their column space is a plane. The column space of this matrix is a plane. What's the relation between the planes? between the two column spaces. They're one and the same, right? It's
Yeah.
the same column space.
Yeah, yeah.
All
Exactly.
I'm taking is here, this B thing that I computed, is a combination of B and A, and A was little a. So I'm always working here with this in the same space. I'm just like getting 90-degree angles in there. Where my original column space had a perfectly good basis, but it wasn't as good as this basis, because it wasn't orthonormal. Now this one is orthonormal, and I have a basis then that so now projections, all the calculations I would ever want to do are a cinch with this orthonormal basis. One final point. One final point in this chapter. And it's just like elimination. We learn how to do elimination, we know all the steps, we can do it. But then I came back to it and said, look at it as a matrix in matrix language, and elimination gave me, what was elimination in matrix language? I'll just put it up there. A was LU. That was matrix, that was elimination. Now I want to do the same for Gram-Schmidt. Everybody who works in linear algebra isn't going to write out the columns are orthogonal or orthonormal, and isn't going to write out these formulas. They're going to write out the connection between the matrix A and the matrix Q. And the two matrices have the same column space, but
I
there's
just got hacked.
some matrix is taking, and I'm going to call it R. So A equals QR is the magic formula here. It's the expression of Gram-Schmidt. And let me just capture that. So that's my final step then is A equals QR. Maybe I can squeeze it in here. So A has columns, let's say A1 and A2. Let me suppose N is 2, just two vectors. Okay, so that's some combination of Q1 and Q2, and times some matrix R. They have the same column space. This matrix just includes in it whatever these numbers like 3 over 3 and 1 over square root of 3 and 1 over square root of 2. Probably that's what it's got. 1 over square root of 3, 1 over square root of 2, something there, but actually it's got a 0 there. So the main point about this A equal QR is this R turns out to be upper triangular. It turns out that this 0 is upper triangular. I could key to this being this R, we get a triangular matrix. The result is extremely satisfactory. That if I have a matrix with independent columns, the Gram-Schmidt produces a matrix with
Determinants. No,
and
this
the
is where it's
connection
going
between
to
those
be
is a
fun.
triangular matrix.
Determinants, Cramer's rule,
That last point, that the connection is a
eigenvectors,
triangular matrix. Please look in the book. You
differential
have to see that one more
equations.
time.
I did some
Okay, thanks, that's great.
differentials. Oh, I'm almost getting closer to doing this. I'm going to take a quick break though. Properties of determinants. Forgot what determinant is. It is what it is. I'm just watching Instagram edits. Imagine. Just determinant. I'm very determinant. I know. Let's just get into it. No more poopty scoop jokes. They're getting fucking.
Okay, this lecture is like the beginning of the second half of this course, because up to now we paid a lot of attention to rectangular matrices. Now concentrating on square matrices. So we got two big topics: the determinant of a square matrix. So this is the first lecture in that new chapter on determinants. And the big reason we need the determinants is for the eigenvalues. So this is really determinants and eigenvalues, the next big chunk of 1806. Okay, so the determinant is a number associated with every square.
1806. Nigga. 1, 2, 3, 4, 4, 5, 6, 7. Eigen, determinant, all of that shit is
So every square
easy.
matrix has this number associated with it called its determinant. I'll often write it as DETA, or often also I'll write it as
Yeah.
A with vertical bars. So that's going to mean the determinant of the matrix. That's going to mean this one like magic number. Well, one number can't tell you what the whole matrix was. But this one number just packs in as much information as possible into a single number. And of course, the one fact that you've seen before, and we have to see it again, is the matrix is invertible when the determinant is not zero. The matrix is singular when the determinant is zero. So that's the determinant will be a test for invertibility. But the determinant's got a lot more to it than that. So let me start. Okay, now the question is how to start. Do I give you a big formula for the determinant all in one go? I don't think so. That big formula has got too much packed in it. I would rather start with three properties of the determinant. Three properties that it has. And let me tell you property one. The determinant of the identity is 1. Okay. I wish the other two properties were as easy to tell you as that. But actually the second property is pretty straightforward too. And then once we get the third, we will actually have the determinant. Those three properties define the determinant, and then we can figure out, well, what is the determinant? What's the formula for it? Okay, can I tell you the second property? That just like scales the determinant so that the identity matrix has determinant 1. Now, the second property is, what happens if you exchange two rows of a matrix? What happens?
I wanna fucking kill you.
So property 2 is exchange rows, reverse the sign of the determinant. A lot of plus and minus signs. I even wrote here plus and minus signs, because this is like that's what you have to pay attention to in the formulas and properties of determinants. So that you see what I mean by a property here. I haven't yet told you what the determinant is, but whatever it is, if I exchange two rows to get a different matrix, that reverses the sign of the determinant. And so now, actually, what matrices do we now know the determinant of? From 1 and 2, I now know the determinant. Well, I certainly know the determinant of the identity matrix, and now I know the determinant of every other matrix that comes from row exchanges, from the identity still. So what matrices have I got at this point? The permutation, right. At this point, I know every permutation matrix. So now I'm saying the determinant of a permutation matrix is 1 or minus 1. 1 or minus 1.
Yeah, either it could go clockwise or anti-clockwise, okay.
Depending whether the number of exchanges was even or the number of exchanges was odd. So this is the determinant of a permutation. Now P is back to standing for permutation. Okay, so if I could carry on this board, I could like do the 2 by 2. So property 1 tells me that this 2 by 2 matrix, I better write vertical bars, not brackets, for that determinant. Property 1 said, in the 2 by 2 case, that this matrix has determinant 1. Property 2 tells me that this matrix has determinant, what?
Minus 1.
Negative 1. This is like 2 by 2. And now I finally want to get, the formula that we all know. Let me put that way over here, that the determinant of a general 2 by 2 is A, D, minus B, C. Okay. I'm going to leave that up like as the 2 by 2 case that we already know, so that every property, I can like check.
It's interesting because this is like so late in the course, and I learned this back in 12th grade. Bro, I learned so much, you know what I mean?
2 by 2. But the whole point
Not like conceptually, but like, is my thing still going on? Okay, it's still going on. Yeah, not really like conceptually, but in a rote memorizing way, you can say. Yeah, I regret it. I regret not watching these kind of videos. Everyone has regrets. It's a part of life. It's a part of life. It is what it is. Can we change anything? Is that even possible? Even if It's possible. Do we really want it? I don't think so. I'd rather live now than think about all of this shit. What a life. Bro, my voice is so fucking retarded. I hate my voice.
Of these properties is that they're going to give me a formula for n by n. That's the whole point. They're going to give me this number that's a test for invertibility, another great property for any size matrix. Okay, now you see I'm like slowing down because property 3 is the key property. Property 3 is the key property, and can I somehow describe it? Maybe I'll separate it into 3a and 3b. Property 3a says that if I multiply one of the rows, say the first row, by a number t, I'm going to erase that. That's like what I'm headed for, but I'm not there yet. That's the one we know, and you'll see that it's checked out by each property. Okay, now so this is for any matrix. For any matrix, if I multiply one row by t and leave the other row, or other n minus 1 rows alone, what happens to the determinant? The factor t comes out. It's t times this determinant. That's not hard. I shouldn't have made a big deal out of property 3a. And 3b is that if I'm always keeping this second row the same, or the last n minus 1 rows are all staying the same. I'm just looking inside the first row, and if I have an a plus a prime there, and a b plus b prime there, sorry, I didn't, I don't know, I'll use an eraser. Do it right, b plus b prime there. You see what I'm doing? This property and this property are about linear combinations of the first row only, leaving the rows unchanged.
Why is that?
Copy alone. Then I get the sum, this breaks up into the sum of this determinant and this one. If I'm putting up formulas, maybe I can try to say it in words. The determinant is a linear function. It behaves like a linear function of the first row if all the other rows stay the same. I am not saying that, let me emphasize, I am not saying that the determinant of a plus b is determinant of a plus determinant of b. I am not saying that. How do I get it on the tape that I'm not saying that? You see, this would allow all the rows, A to have a bunch of rows, B to have a bunch of rows. That's not the linearity I'm after. I'm only after linearity in each row. Linear for each row. Well, you may say, I only talked about the first row, but I claim it's also linear in the second row. If I had this, but not, I can't have a combination in both first and second row. If I had a combination in the second row, then I could use rule 2 to put it up in the first row, use my property, and then use rule 2 again, put it back. So each row is okay, not only the first row, but each row separately. Okay, those are the three properties. And from those properties, so that property is 1, 2, 3. From those, I want to learn a lot more about the determinant. Let me take an example. What would I like to learn? I would like to learn that, so here's a property 4. Let me use the same numbering as here. Property 4 is if two rows are equal, the determinant is 0. Okay, so property 4. Two equal rows lead to determinant equals 0. Right. Now, of course, I can, in the 2 by 2 case, I can check, sure, the determinant of AB comes out 0. But I want to see why it's true for n by n. Suppose row 1 equals row 3 for a 7 by 7 matrix. So two rows are the same in a big matrix. And all I have to work with is these properties. The exchange property, which flips the sign, and the linearity. And all I have to work with is
why is this nigga looking like that?
these properties. The exchange property, which flips the sign, and the linearity property, which works in each row separately. Okay. Can you see the reason? How do I get this one out of properties 1, 2, 3? That's all I have to work with. Everything has to come from properties 1, 2, 3. Okay, so suppose I have a matrix, and two rows are equal. How do I see that its determinant has to be 0 from these properties? I do an exchange. Property 2 is just set up for this. Use property 2. Use exchange rows, exchange those rows, and I get the same matrix. Of course, because those rows were equal. So the determinant didn't change. But on the other hand, property 2 says that the sign did change. So I have a determinant whose sign doesn't change and does change, and the only possibility then is that the determinant is 0. You see the reasoning there? Straightforward. Property 2 just told us, hey, if we've got two equal rows, we've got a 0 determinant. And of course, in our minds, that matches the fact that if I have two equal rows, the matrix isn't invertible. If I have two equal rows, I know that the rank is less than n. Okay, ready for property 5. Now, property 5 you'll recognize as a key. It says that the elimination step that I'm always doing, subtract some multiple L times row 1 from another row, row K, let's say. You remember why I did that? In elimination, I'm always choosing this multiplier so as to produce 0 in that position. Or row I in row K. Maybe I should just make very clear that there's nothing special about row 1 here. Okay, so that, you can see why I want that one. Because that will allow me to start with this full matrix, whose determinant I don't know, and I can do elimination and clean it out. I can get zeros below the diagonal by these elimination steps, and The point is that the determinant doesn't change. So all those steps of elimination are okay, not changing the determinant. In our language in the early chapter, the determinant of A is going to be the same as the determinant of U, the upper triangular one, that just has the pivots on the diagonal. That's why we want this property. Okay, do you see where that property is coming from? Let me do the 2 by 2 case. Let me do the 2 by 2 case here. So I'll keep property 5 going along. So what am I doing? I'm going to have AB, CD, but I'm going to subtract L times the first row from the second row. And that's the determinant. And of course, I can multiply that out and figure out, sure enough, AD minus BC is there, and this minus ALB plus ALB cancels out. But I just cheated, right? I got to use the property. So what property? Well, of course, this is I'm keeping the first row the same, and the second row has a C and a D, and then there's the determinant of the A and the B, and the minus LA. And the
A and the B and the C and the B and the...
So what property was that? 3B. I kept one row the same, and I had a combination in the other row, and I just separated it out. Okay, so that's property 3. This is by number 3. 3B.
What the fuck am I looking at? Properties of determinants. What even is a determinant, man, niggas? What even is this? Determinant. Is this Tamil? If it's not Tamil, I'm flipping out.
आजको क्लासमा हामीहरू डिटर्मिनेन्ट एक्सप्रेसेस A, B, C, D छन् भने
Yeah, these guys like don't
क्लासमा हामीहरूले
instinctively understand determinants, do they? They just like do sums all day, which computers can do it. And now to sound like a boomer, but it's like, bro, computers can do it. Like, we need to like conceptually understand all of these concepts, and then go on the side by side. You could like use Python and all of that. I do that sometimes, but yeah. If you don't have the conceptual understanding of what's going on, it's going to be really difficult. Let's just see this.
Let's go back to the basics. Determinant.
Ooh, bro, look at how many videos on determinants.
Let's take a matrix of 1, 2, 0, 2, 1, 0, 0, 0, negative 3, and let's use this matrix to transform every vertex on a unit cube of length, width, and height 1, aligned along the x, y, and z axes. After transformation, you'll see that we have a completely different object than we had before. But now I have a bit of a question. How much larger is this new transformed object? We could solve this problem with numerical integration by encapsulating both objects in a larger cube and performing Monte Carlo integration. After integration, we can say that the larger object is about 9 times bigger than the unit cube. Now, let's think of this problem a little differently. During matrix transformation, most vectors will stretch and rotate. However, there are certain vectors that only stretch and do not at all change direction. These vectors are known as eigenvectors, and the amounts by which they stretch are known as eigenvalues. If we align the sides of our unit cube along these eigenvectors and perform a matrix transformation on each vertex in the cube, we'll find a rectangular prism that has not been skewed at all. This makes finding the ratio between the new transformed object and the original unit cube kind of trivial. It's simply the length times width times height of the new cuboid. Now, because we align the unit cube along eigenvectors, and each side of the unit cube is of length 1, after transformation, the new length, width, and height are all eigenvalues. So, how much bigger is the object after transformation? Well, it's simply a product of all of the eigenvalues, which, in this case, is exactly 9. Here, I suppose it makes sense that any object's volume will increase by the amount of stretching in each dimension, which is exactly what we said before. The new volume is a product of the eigenvalues.
Now, at this point, you might be thinking that we're pretty clever, but mathematicians have at least one more trick up their sleeve. Determinants.
So let's do it. Let's find the determinant of our transformation matrix. It will be 1 times 1 times negative.
Bruh, we know this, okay.
Or
fucking nerd.
exactly 9. the same as we saw before.
Dork!
And that's
Dork
a
alert!
simple determinant can be determined by comparing the new
Dork! Shut up. Bro, why am I getting all these YouTuber motherfuckers? Like, I don't like you guys. Jacobian. The right way to think of derivatives and integral. I'm gonna... Fuck, I need to like... No, don't. Fucking hell. Can you do that for me? Can you like... Yeah. What is a determinant? Who knows?
Derivatives. When we first learned this concept,
Brother, these motherfuckers are smart. Determinant. What even is a determinant, bro? Brother, this guy stinks. This guy is like so much smarter than me. Isn't that crazy? This guy is so smart. Look, bro, you can be smart, but it's like you're a pussy. You know what I mean? I don't know. I don't know. I don't know. Can he be strong? Can he like bench press 225? That's the true strength of your intellect. If you can't bench 225, doesn't matter. Doesn't matter. You could be a Nobel Prize winning scientist. Doesn't matter, bro. In these streets, it's different. Okay? The rules are different out here in the streets. So don't fuck with it. Bro, donation. Motherfucker like gave like 40 rupees. 40 rupees. Yo, you can have this 40 rupees, bro. Yo. He didn't even like it. It was like, bro, fuck this. 40 rupees. You fucking kidding me? Fucking kidding me, bro? Bum ass nigga, 40 rupees. Okay, let's say I'm gonna end the stream right there. I'm gonna come back, do some shit. Yeah, do some determinants and eigenvectors. Hopefully, I can like get through the 2 chapters pertaining to determinants. Get a deep understanding on what determinants is and all of that. Until then, stay juicy.